Good morning, everyone. It will be my great pleasure to be there with you in Almaty and having the possibility to share the discussion lively. Unfortunately, we have to record this meeting, this discussion, this presentation, but I will be there with you just after the 25-30 minutes of presentation for question and answer. So I'll see you very soon live. In the meantime, please enjoy this presentation, and I will start right away with the slides. I'm sharing the screen, and here we are. You should be able to see the first slides. And as you see, you are going to have a direct translation of the language from English, let's say broken English with an Italian accent on it, into Russian for your commodity. In the meantime, there will be oral translation as we go directly in the language that will be more comfortable for you to listen to. Today, the discussion that I would like to provide is a sharing of an experience about opportunities for precast concrete to be used in the Central Asia. So we are not only referring to Almaty region, and we're going to look at the Kazakhstan, obviously, seismicity and the seismic map, but we're going to discuss about, generally speaking, opportunities worldwide, which could be also in Central Asia a way to go. We're going to look at new technologies for concrete in the precast concrete way, or prefabricated concrete, as it was the old way to say. But we're going to also show real buildings applied around the world using this technology. So we're going to discuss about what they look like in terms of beam column connection or wall-to-wall connection. They might be coming both seismic resisting systems, so you can have an open space. And we're going to discuss about resilience, so about the possibility to not only provide a nicely looking, architecturally speaking, building with high functionality because of the open space, but also resilience from the highest level of seismic resistance. So the capability to provide your community, our community, with a better capacity to bounce back after an earthquake disaster. If you're looking at the map of the world, so the earthquake map, unfortunately, let's say we like to live as human beings in the most critical regions. They are beautiful, and that's exactly why humans are very often tending to go to those places. If you come to my place, Italy, and we go through the yellow dots, which are the highways, I will keep going until a certain point. I've already passed on Kazakhstan. I will keep going. You can see that the whole world is connected by these highways of earthquakes, which are basically the boundaries of the place. You are specifically over here. So today we are discussing about we are physically in or virtually in the Almaty regions in Kazakhstan. And if you go to see what has been the history of earthquakes in Kazakhstan from 500 to 2009, so let's say 1,500 years, there are quite a number of substantial earthquakes. Magnitude 7, you can see the green ones, magnitude 7.5, and even magnitude 7.5 higher, going to 8, especially in the southeast region and in the southwest region, which is where obviously the boundaries are getting into, boundaries of the country are getting into the very high level of high seismic region. If we go to see the seismic map using a peak ground acceleration, which is a typical way to describe the earthquake intensity everywhere around the world, and very recently, like everywhere else in the world, Kazakhstan has been provided with a PSHA, probabilistic seismic hazard map, which allows to calculate the probability of occurrence of an earthquake of a certain intensity within the lifespan of the building, so of the structure. It can be 50 years, and typically in 50 years, we are looking at the probability of exceedance of 5%, or 10%, or 2% in 50 years. And typically the design is for a 475 years return period, so 10% in 50 years. But what I want to show you here is a little bit higher earthquake, quite a little bit higher, which is the 2,500 years return period. So an earthquake which is supposed to have an exceedance of 2% in 50 years. If you think about 2% in 50 years, you're looking at a lifespan of a building, or a lifespan of 3 generations, which is 100 years, it's going to be 4%. and the design level is going to be 20% of a probability of occurrence for the design level of earthquake. So the level of peak ground acceleration are quite substantial. So they're getting in the yellow zone, and they're increasing the more we go to the southeast. And in fact, Kazakhstan has been struck by very, very strong earthquakes of magnitude 7-ish high. So 7.3, 7.5, 7.9, 8. In the, especially in the end of the 1800th century, in the Almaty region especially, there was a major earthquake, also called the Verni earthquake. And later on in 1900, the early 1911, there was probably the one that has been the biggest one recorded. It was in the border with Kyrgyzstan. It's also called the Kermin earthquake, and that type of earthquake event caused substantial amount of collapse and so forth. So the region of Almaty, or not only Almaty, but I would say the whole Kazakhstan itself and the Central Asia, is definitely very prone to very severe earthquakes. If we look at what can precast concrete provide us with, or provide the community with, precast concrete in seismic regions has been for a while, look at the text, has been limited in the use and development basically everywhere around the world for few reasons. First of all, lack of confidence. The performance of precast concrete buildings because of detailing, because of design issues, not because of the material, has not been adequate as people would have liked to see. And so people lost confidence on the behavior of precast concrete in seismic region. But also there was, generally speaking, the absence of rational seismic design provisions. So typically we are in the 1990s, and then later on things improved. In the 1990s, people were not very confident, comfortable with using precast concrete in seismic regions, and there was a lack of knowledge. Lack of knowledge means lack of seismic codes, but means lack of education. So it was not being taught in the universities and so forth. So very few engineers, very few architects were able to specify precast concrete in a proper way for seismic design. Later on, what happened? Typically, the trends was to either avoid precast concrete or to allow for precast concrete if precast concrete had used an emulative approach. We will going to see what emulative approach is. It's an emulation of cast-in-place concrete. It's something whereby precast concrete connections are being joined together using a cast-in-situ approach, and that has been a way to deliver precast concrete in seismic region in a quite proper way. Alternatively, there was another possibility, which is still very, very much available, and I would like to explore that with you. Strong connection. You connect precast concrete not where the inelastic mechanism from seismic action will be, but far away from that. So we're going to see what it looks like. But there is a third level, and that third level is really breakthrough. It's a milestone in earthquake engineering, which has been applied in precast concrete and later on also in other materials. So it's about jointed ductile connection. It's new. It's blue, new. So jointed ductile connection is a different way than the old precast concrete for industrial plants, than the emulative way, which is a little bit less old, but still obsolete enough when compared to this revolution, which I will be delighted to explore with you. And I'm showing now the Russian translation to appreciate more what jointed precast, jointed ductile connection will look like. Now, let's discuss about some fundamental aspects in seismic design of precast concrete. Precast concrete itself can be designed very properly if you know what you're doing, as per any other material. So you do need to have a design methodology which is appropriate. And it's not just a force-based design, as typically people are using, but can be also a displacement-based design. So something whereabout we are trying to limit the deformation of the building, and we're trying to design for a given earthquake such that the extent of drift, the displacement between two stories divided by the height, is called drift, and we should be knowing it, or the amount of rotation of a certain element are going to be limited. So we are designing for a specific amount of displacement, no more than that. Generally speaking, we need to understand the overall behavior. The structure system itself, the diaphragm, the non-structural elements, the foundation. I mean, the whole system has to be delivered the seismic response as a package. It cannot be just one element or other elements. So there should be a load path, the possibility of moving the stresses through the structure in a proper way. Detailing is fundamental. The connection detailing between an element, a member, a beam and a column, a wall and the diaphragm and the seismic resisting frame and so forth needs to be properly done. Typically, when we are adopting a casting situ approach, we are thinking that casting together will be making everything monolithic. So it will be strong, stiff, and robust. But that's not exactly what we need to do. We need to provide capability to deform in a ductile manner. So we're discussing about ductile behavior and possibly dissipation capacity. Not necessarily a building designed as a bunker, so a very stiff type of robust building is the best way to go. Nowadays, we're preferring to design for a less stiff, less massive type of building for economical reason also, as long as we're able to limit the damage. We're going to discuss that. So detailing is fundamental, as well as fundamental becomes robustness. Robustness and redundancy, they're not exactly the same thing, but means that after an earthquake, during an earthquake, we do have a different alternative load path. So the opportunity and the possibility of our building to resist the earthquake is going to be provided by different, more than one type of element and structural system. And also, if something goes wrong, there is a plan B. There is an opportunity to back up the behavior of the structure, because you're not relying upon a single structural system, you're not relying upon a single load path. Displacement compatibility, the compatibility of the movement between the seismic resisting system and the gravity system should be checked very carefully. So it's not about only strengthening a building with some elements, but it's about checking the full movement of everything. At the end, it's about detailing, detailing, and detailing. So really at the end of the day, we need to provide a system whereby the detailing is the devil which we have to fight against. Otherwise, things can go wrong. If detailing is being properly done, that will count more than any computational model that you can provide, because computational numerical model, let's remember, they actually do mathematically what you input. If the input is not good enough, the output of the mathematical model will not be good enough. But detailing, using conceptual design as a proper engineer would do, is fundamental for a good behavior in a seismic region. We are going to start about looking at hinge connection, the old way. And I'm going to show you what has been done everywhere in the world, including in your own country, very specifically, typically for precast industrial buildings. This type of construction is very, very powerful. For gravity design can allow you to go for long span. It can have beams sitting simply on corbels. These corbels are driving the forces to a cantilever scheme, which is not optimum, but that's what was the solution. And so a cantilever column is actually the seismic resisting system only with simply supported beam, not coupling the behavior. These systems are very good for gravity loading, but not good for earthquake loading. And this is what we unfortunately found. But we would like to explain here that we don't have to throw away everything here. It's a matter of detailing the connection between beams and columns. And if we can do it in a different way than just sitting on a corbel, sitting on a friction corbel, or maybe using a dowel action, if we can improve that connection between beam and column and between column and foundation, and we can make the system more robust, that will be the way. And so this solution number one, which has been the oldest one and not very appropriate at all for seismic region, I would like through the presentation to show you the evolution of hinge connection into something more, and will be option 2, and into something even more, which will be option 3. Now, we do know about industrial buildings, precast car parking can be malls, can be warehouses, can be department stores. There are large column-free type of buildings, and the idea was to actually push for pre-stressed and precast concrete elements, which could go for a long span. The problem of this solution, though, is that you do not have a proper moment-resisting connection. So the advantages are quality control, speed of erection, dry construction. You can go fast. You can have a good quality control off-site, so in your plant.
once you go to the building site, you do not need to have a specific, very high-skilled crew to make the construction. You only need riggers, which are people capable of using a crane and mounting, if you wish, a Lego type of construction system. But these advantages are undermined by very important limitations. The limitations are that the structural system themselves, they are not well connected. Actually, they are even not connected, or they are connected in a way that is not efficient. So the structural scheme is not capable of providing moment resistance. So we do need, in seismic region, to provide moment resisting capacity between one connection and the others. Otherwise, the system will be too weak under lateral loading. It would be very good for vertical loading, gravity loading only, but it would be very weak for lateral loading. So let's see what has been developed few years down the track after the old way of doing things. These are examples of emulative approach. And you can appreciate that since the 90s, late 1970s, late 1980s, in the Europe, East Europe, Central South Europe, so the Southern Europe is very high seismic, Central, South, and East becomes again seismic again. If you wish, if you can go to another different place, Japan, New Zealand, and you will find that this type of precasting made of the dark gray is precast, made of semi-precast elements connected together with a cast in situ connection. So there are precast elements which are then made monolithic, if you wish, by using cast in situ, which we call wet connection. And there's been plenty of alternative solutions for that. And I want to show you some of the latest developments in terms of bulletin of the FIB, the International Federation of Concrete, which I strongly recommend you, if you don't have any of them, to start looking at those bulletins and becoming a member, because you can get a very interesting solution being explained from a conceptual design point of view, from a mechanically modeling point of view, from a numerical model point of view, and you can see behavior, guidelines for better design, and more so about durability, technical hardware, detailing, connection, and technology. So you start from a column, and you can have, in the emulative approach, have a precast beams sitting on the corbel, and then you're going to have a cast in situ connection of the whole system. Then you're coming, the beam can be a rectangular type or can be a U shape. We call it shell beam. Then you're coming with the flooring system. The flooring system is supported on supports, on shores, and then you're going to have a cast in situ of the topping. We call it the topping. So the diaphragm action will be working through a welded wire mesh or a much more proper reinforcing detailing on the flooring system, and the whole system will become monolithic. But it started from a precast being connected together with a cast in situ approach. Now, these are examples of what this emulative approach would be. And I'm on purpose, I'm going back to L'Aquila. By the way, you would have, of course, noted the screen behind me is the Colosseum. I'm calling from Rome, the University Sapienza of Rome, where I'm now working. I've been traveling around the world in my career and my life, from Pavia, from Italy, university, northern part of Italy, to California, San Diego, and then 16 years in New Zealand, and then back to Italy in Rome. And the reason for which I'm showing the Colosseum is not only because it's marvelous, but because it's actually an example of precast, of a prefabrication, which looks like a precast concrete frames in the older ages. And I will explain you how, by taking some hints, some suggestions from that way of doing prefabrication, we can deliver a much higher performing, low damage seismic resistant system. This is option 3, which I'm going to show you later on. But these are examples of the emulative approach developed in Italy after the L'Aquila earthquake, shell beams, which are being connected together with the other elements with a wet connection. And they can do an excellent job in providing semi-precast elements to become more moment-resistant connection. But there are consequences and limitations. Let's stay on the positives. These are other examples in Turkey, Istanbul, Thank you to Yapi Marchesi Prefabrication. Again, a solution whereby the big corbels in precast might remain there. If you are used to do precast concrete in such a way, don't throw it away. It's actually quite good, very good for gravity, quite good, generally speaking, not good enough for seismic. But if we can improve the detailing by having, you see, the connection between beam and columns done in a way that you can then wet cast the connection itself, then you can provide a moment-resistant connection. And these are examples from India. So I wish you please send me some of these examples of precast concrete buildings using a emulative approach in your own country or in your own, if you are from Almaty region. So we will be able next time to explain around the world that this emulative approach has already been also adopted in your own country. What are the limitations of this connection detailing based on emulative approach? Precast, and then precast, and then wet connection. They do not exploit the advantage of precast concrete. So basically, you're not able to go fast as you could because the precast concrete is being slowed down by the waiting of the casting of the wet connection to cure. So you have to wait a bit. Also, slowing down the erection speed means higher cost. Means that your client is paying more, that your mortgage on the building it costs more, that you have to wait to sell the components, the apartments of the buildings, and so forth. But also, the connections are quite complex. They are not simple. Those type of connections themselves, they require quite a manufacturing skill and, if you want, in the plant, and time. Skill and time means, again, money. So what, in addition, we would have is that a traditional system, emulative system, will form a plastic hinge. The plastic hinge is a typical way of any concrete building or any steel building to survive from an earthquake. So it's the way to damage in a plastic manner the connection between elements and elements through that plastic flexural type ductile behavior. So the idea is that if you deliver a precast concrete solution with the emulative approach, you would have necessarily almost unavoidable damage. And we don't want to have that, but this is what every code in the world allows us to have. So I want to show you something which is a dramatic experience that I unfortunately lived through, or unfortunately I lived through. So I'm here reporting back to you. And in Christchurch, in New Zealand, we are going to the other side of the world from Italy. We are nearby, more near to you. In 2010, 2011, there was a series of earthquakes, specifically the 2011 one, 22nd of February, destroyed the city of Christchurch. That type of earthquake caused quite a number of victims, 186, but caused also a significant social economical impact because the whole city, the CBD, the central building district, got destroyed. So I want to show you an example which has been an exceptionally good example of a 22-story precast concrete building designed in the 80s. Excellent design, which today we are still using as an example of best emulative approach made of precast concrete. You can see here the precast concrete elements. They are getting connected together, as you can see here, in the quarter, fifth of the span, or in the middle of the span, where the moment capacity, moment demand, to say better, is going to be lower because of the seismic action. This earthquake pushed the building to the limit. And so the earthquake itself showed that the building was designed very properly. The building developed those famous plastic hinges. We call them plastic hinges in the beam. Any new design around the world will rely upon these plastic hinges in the beam. The problem is that after you have this plastic hinge in the beam, you don't know how to repair it. And if we make a comparison with a car, a crash test, no one will be surprised to see in a crash test, or to remember that in a crash test, our car is destroying locally the plastic, in a plastic behavior, the front part to protect the pilot. So the car is actually plasticizing in a specific region, which is designed specifically for that purpose. And the purpose is survival of the pilot, which we will call life safety. In our seismic design, we call this life safety. So what does it look like? In a numerical model, which nowadays we are able to perform, since quite a while we're able to perform, now we're able to go faster. This is a representation of our plastic hinge in our car crash. It's not a car crash, it's an earthquake crash against our building. So our building is going to go through the earthquake crash, is an earthquake crash test, and is going to develop that plastic fuse. That plastic fuse is allowing the building to protect the life of the inhabitants, but not to protect itself. So what it was not clear for quite a few decades, when people were improving, where human beings were improving the seismic resistant philosophy, and were able to actually concentrate the damage into a specific location instead of allowing the building to collapse. It was a major revolution in 1960, and it did come from New Zealand. Park and Pauly developed what we call hierarchy of strength or capacity design. The theory of the chain that Tom Pauly was using was mentioning that the weakest link of the chain makes the chain strength. So the strength of the chain in tension is actually due to the weakest link. If the weakest link is ductile, you're going to have a ductile mode of failure. If the weakest link is brittle, the whole chain will be brittle. It doesn't matter what the other links are going to do. So in the 1960s, we changed completely our way of designing for earthquakes, because instead of having small columns and big beams, Park and Pauly suggested to have stronger columns and weaker beams, to the point that the weaker beams was supposed to have this plastic hinge. And that's exactly what we've been doing. Very properly, we have been designing for plastic hinges in specific region. Let's go back to remember what these plastic hinges are doing. They are protecting not the car, they are protecting the pilot. They are doing their job for life safety. And that's exactly what we're doing. We are designing for life safety. So after the Canterbury earthquake, the earthquake in New Zealand 2010-2011, people discovered that the seismic design philosophy, as we knew, they were great but not sufficient enough to protect a city, to protect the community, because the impact of that type of damage is no repairability, so you are not able to repair it. And this is a picture from a photo taken from the plane, showing the CBD. This sand over here were buildings, where many people were living. Luckily enough, as I mentioned to you, the number of victims, 186, could have been thousands if the buildings had been designed according to older codes, but they were designed very properly. Yet they were not able to protect themselves. So we had a city which was not able to protect for itself. The cost for the population for the whole country was 25% of the gross domestic product. So we are not able to afford, as a single family, as an individual owner or multiple owner of a building, as a city, we are not able to sustain such a disruption of our community in the long term. Of course, the most important part remains life safety. And of course, we need to deliver modern building capable of providing life safety. But precast concrete can do that, life safety sort of a protection, but can do even more. And that's exactly what I'm going to show you. What has been so far shown is the standard 2024 state of art of seismic resistance that we are able typically to provide. But we need to do something better. I don't know if you're familiar with this is becoming more and more common, the discussion about resilience. But typically people don't show what resilience means, which is this over time capacity to react through, against, or after, in the aftermath of a disaster. The disaster can be anything, can be an earthquake, can be a hurricane, can be the pandemic COVID-19, can be anything which is attacking and disturbing, destroying, impacting significantly a person, a family, a city, a building, a community, a country, and the whole world. So you receive an impact that you're trying to get out, try to recover back to a new position, which is called new normal. That's new position. The faster you're able to get out of that big hole that you've been thrown into, so the better it will be. The resilience is best if the area of this big hole is the lowest. So the less impact you have and the easiest and faster you can go out of that hole, the better it is in terms of resilience. So basically, we need to focus on reducing the impact. As simple as we need to put all our effort in providing seismic resistant buildings, which are capable to not only receiving small damage, bigger damage, and bigger damage, the bigger the earthquake. These are typical performance metrics, which is available in 1990s. I know that I'm going faster in my discussion, but there will be plenty of time for you to recheck back, including the recording, and then I will be providing you with some text for reading to understand what's going on. Typically, we design a building such that for a small earthquake, frequent type, we get fully operational. For a larger earthquake, we get a little bit of a damage control, a little bit more than a damage, but it's repairable. The bigger the earthquake, the more we are actually looking for life safety. So we are accepting high level of damage, but we are accepting also that the building might not be repairable. So the repairability is becoming a very important condition. It's becoming actually a criteria that in the FIB new model code, the model code of the FIB, International Federation of Concrete, 2020, has been just released and published. Please go and check. You're going to see that we are discussing about repairability as a fundamental component of sustainability of a society. So in a way, if this was your house, this was your building, this is what we are designing an earthquake-resistant design for. And this is what you are believing we should be receiving and delivering. So people think about earthquake-resistant being that. We are actually delivering something completely different. People don't know. So the code is written as a minimum by law. We are actually designing by minimum by law, and we are delivering a car which is crashing and is actually receiving a ductile plastic behavior in a component of it. So it's not possibly repairable. What is the controversial issue here? People, yourself, me, citizens, think about earthquake proof. We think about a building which is capable of going through an earthquake and be unscathed, have absolutely no damage whatsoever. You receive an earthquake and you get a little bit of a shaking, or actually a big shaking, but you are not concerned anymore. Your building is supposed to stand, you're supposed to continue. This is what we dream to have, which is an earthquake-proof building. That's not what we have by law. By law, everywhere in the world, we have a seismic-resistant or an earthquake-resistant building, which is exactly different from very far away from earthquake-proof. It's not an earthquake-proof. This car over here, no one ever thought about calling this car anti-accident or accident-proof. No one thinks a car is accident-proof. People hope that is life safety proof. So it's actually death proof. Is actually capable of providing life safety, but we don't think about the car being repairable after a major crash. We do need to start thinking about what to do for earthquake-resistant building, because if they were like normal cars, which are not repairable, then we will be following the same path of what happened in New Zealand, which is a very high-level modern country. So let's keep going fast and quick. What should we do? We should be targeting, I'm actually pushing on the left-hand side from your part, we should be targeting a higher performance. In a nutshell, we have to raise the bar. We need to design a building such that the building itself will be protected from a crash test, not only the people living into the building. This means something which can be a problem. If it is going to cost too much, then people will not be doing it. If it's going to be a matter of designing a nuclear power plant instead of a house, obviously it's not going to happen. So I give you good news. The good news is that people listening in real life in Almaty or virtually remotely, we do have the technology in 2024 to raise the bar and to create almost, not exactly the, almost earthquake-proof building. We do not have an earthquake-proof, but we are able almost to get there. And Precast Concrete has the solution to make it happen. So going back a little bit, slowing down, going back a little bit to the presentation of today, it's about opportunities from Central Asia to use Precast Concrete. And I'm telling you, that precast concrete has been used widely and fantastically in every country in the world in some form of option 1, but in seismic region it doesn't work. With option 2, which is great, and I would be suggesting you to at least use option 2, which is the cumulative approach, but in seismic region is not sufficient enough. There's going to be a cost associated with the repairing, which we don't want to have it. So what will be the next level up? And that's exactly where we're going. Joint ductile connection. We call them low damage technology. Low damage technology means that after an earthquake, we would like to have low damage in the car, in the building, and we should be able to repair it without too much cost. There's a new generation of seismic resistant, which I don't call earthquake proof, but they are very, very nearby to become earthquake proof. They are low damage. We call them low damage. This low damage seismic resistant system has been developed starting from the late 90s, so we're going back 25 years ago. In United States, big project coordinated by Professor Nigel Priestley, which was a top professor in earthquake engineering, #1 in the world at that time. Park and Paul in Priestley. Park and Paul were in New Zealand. Priestley was a student of them, PhD, and then lecturer, and then professor, and then engineer and professor, working with them as a PhD student of Park and Paul. Then he got recruited in San Diego, in California, in the 1980s type. And at that time, he developed through a major project with the precast concrete industry in the States, a new solution, a new way of working on it. Thanks to an amazing team. I'm referring to John Stanton and Susie Nakaki, for example, who tested with plenty of other people this 5-story building in San Diego. It's a 5-story building which was tested as a largest test using precast concrete with with a revolutionary approach, not emulative, and I had the honor in 1998, 1999 to be part of that. This is 25 years ago myself, and this 25 kilograms ago, if you wish, myself, but I still maintain the same passion and the same enthusiasm for novelties. So learning from those ropes in 1990s, what are these type of connection? There's quite a lot of the, let's say, legacy that has been implemented into this connection. They are dry, they are elements connected through tendons. So we are basically using the same concept of post-tensioning, which has been adopted for bridges. This post-tensioning, though, is unbonded. So you're not completely bonded between concrete and steel. You're using PVC duct, so they can actually move these tendons and slide through such that they are like an elastic spring. This elastic spring during the earthquake will be loading force and then springing back, loading, springing back. And so there's no way basically to damage it. Let's see what it looks like. You're either in a traditional concrete approach or in a cast in situ emulative, you're going to break back and forth, and you're going to have damage, this famous damage which we don't know how to repair. In the new generation, the terminology is rocking. Rocking is actually this lifting up and coming down, lifting up and coming down. And by doing this lifting up and you're tensioning the spring, you're basically able to go through an earthquake without damage or with low damage. Where does it come from? I told you that there is a reason for which I was using the Colosseum today, not only because I'm in Rome, but because this way of constructing was one of the best reason for which we are able now to develop a modern low damage technology. This is a Greek temple. We are in the ancient Agora in Athens. So the Agora is over there up in the Acropolis. We are lower, in the lower part of the city, of the ancient polis, the city. And this temple is able to go through an earthquake by rocking, by having multiple rocking systems between each other. So this has been revolutionary, taking that type of rocking system, adopted into a rocking post-tension new modern way of doing precast, is literally a milestone in earthquake engineering. If the first milestone probably in earthquake engineering, one of the main one, was the capacity design of hierarchical strength, that I mentioned, in New Zealand from Park and Paul, Professor Park and Professor Paul, at University of Canterbury, New Zealand, which I then not coincidentally, I happened to go because it was a fantastic place to go and learn, and I stayed there for 16 years, 16. So if the capacity design was a way to protect the small columns and big beams, making the columns larger, then the next step up was to make the weakest link of the chain not only ductile, but also repairable. And so we started doing this type of evolution. In the pre-70, older type of beam column connection were breaking in shear. In new connections, they actually break in a nice way in a plastic hinge, but we don't know how to repair them. And in the newer way, the rocking temples, we are able to go through an earthquake with less damage. The next level up became repairability. We called plug and play. This sort of a piece of steel which is being placed from inside to outside, and it's a fuse. You see there's a fuse? So it's actually like an electrical fuse. Instead of being called electrical fuse, it's actually a seismic fuse. And this seismic fuse, which I developed, I did not patent, so you are free to use with my team. We developed, we tested, and without patent, you are allowed for free to use it. What does it happen? This fuse can become a gadget. You create a fuse, you place it inside an anti-buckling tube, and then you fill with epoxy or with mortar. And this becomes your new armor. It costs $15, $20. So it's really a cheap way to provide external armoring or external steel instead of internal steel. After an earthquake, as similarly to what we typically do, we are changing light bulbs in a normal day without being an electrical engineer. Everyone after an earthquake will be able to change the plug and play devices, plug and play fuses, without being an earthquake engineer. You can go to the supermarket and you buy your extra small, or whatever size that will fit within your living room, bedroom, bathroom, and so forth. So this is the extent of earthquake-resistant technology evolution. Let's call it progress. The progress in earthquake-resistant technology has been unbelievable. This is all my research team in New Zealand. We have been pushing hard 20 years ago, 2004, 2005, 2006, and keep going with not only beam column joint connection, wall to foundation system connection, bridge piers to foundation system connection with different type of architectural features of the plug and play, but also we prepared many experimental testing, which became real building in the real life. So let me show you what you should be able to hear the sound. Let me show you what this test of an earthquake almost looks like. There's a pulse tension here, it's a precast piece connected with a precast column, and there is a rocking system, which I will show you the next level up in the next slide. There is no damage whatsoever. So if we go to the zoom, you will appreciate this movement. So you see the opening of the gap means air is opening, there is no damage. Again, there is a precast concrete column, there's a precast concrete beam, and there is a tie, horizontal post tensioning, tying together the whole system. So this is the way to reproduce the ancient Greek temple and make it in a modern engineering way. And we are able to deliver the best solution for the community, which is an earthquake resistant as they think. Now, how can you design it? Feel free to go to see the FIB bulletins. And so FIB Bulletins 2004, that was prepared by Bob Park as a chairman and Fumio Watanabe-sensei from Japan. And I had the honor to be part of, as a young fellow, to be part of that committee. And then more recently, with our great friend for everyone in a large committee, the friend is Professor Spiros Tsoukantas, a Greek engineer and professor. He did an amazing job, not only in Greece, not only internationally, but also in India. He pushed hard to get India updated to precast concrete. So if he was here, I was certainly would have been delighted to have a co-presentation with him to show you the latest discussion that we had implemented in the FIB Bulletin 2016 about detailing for precast concrete in seismic regions. We do have a code. The New Zealand Code 2006 has the opportunity to design this type of technology, and we did deliver a design example. It's in English. We can provide, maybe we can think about it to provide a translation for your own engineers, but we have a full design of a 5-story building as a design example, made of walls, precast walls, made of precast concrete frames with this post-tensioning, with this rocking system. From theory to practice, fast and quick. There are buildings everywhere around the world. This is the highest 39-story building, 39-story building in San Francisco. Is still the highest. This is what I've been developing with colleagues in Italy, and it's in Italy in much later on, just to show you that from not only US, but we managed to do it also in Italy. People have been following the ropes and applying in Argentina, in Costa Rica, and then in New Zealand, obviously, it was us pushing very hard. This is the first in the world that we applied using the plug-and-play devices in Wellington. These buildings, which are really nice and neat during construction because they are self-standing, it really is like a Lego system. And that's a younger me with 2 colleagues, Alistair Katanang and Adam Thornton, directors of the engineering consulting that we work with. Another building that we designed actually went through the earthquake. There was I don't have the time, it was a different way of designing, but it's still post-tensioning, precast, dry connection, but you're going to use nothing else than what you're used to. So hollow core floors or double T's, and through the earthquakes, this building performed extremely well, to the point that no damage whatsoever occurred to the whole building itself. That was actually used as a hospital, as a private hospital, and it went on the media. So the media was asking, what is this? How does it work so nicely? So everyone wanted to or many people got aware of this type of technology, and more people wanted to have this type of technology, not only after the earthquake, even before, to be honest. This is another building that I've been designing with colleagues in New Zealand, and it's a Rotorua police station, northern part of the country, so North Island, and you can see here the plug-and-play devices, which are in the middle of the corridor. A fantastic, beautiful design. We presented that at the World Conference in Earthquake Engineering in Japan, and this is the Central Library in Christchurch. This Central Library in Christchurch, which is an amazing architecture feature, is using precast, heavy precast concrete walls with post-tensioning, with different type of dissipation, connection detailing, a masterpiece plug-and-play to be able to deliver the seismic resistance. And the most important part is actually how it got constructed. We wanted to have, the solution was to have segmental precast walls being post-tensioned together, but it was easier and more efficient, not easier probably, more efficient, to have a precast casted on the site. So the precast walls were casted on the site, and they were then lifted up in place to make it happen. I want to show you a last video. We imported this technology into Europe. I got granted as a principal investigator a big project to be able to go onto a shaking table and to show a full multi-story building, a 2-story building in this case, as a mock-up building with envelope, not only with a structure system. So we have frames, walls, facades made of precast concrete, heavy facades, as well as partitions and glass facades. Look at the experimental test over here. We tested using a collapse type of level of earthquake, so an earthquake which should collapse almost a new building. You take a new building, you design a new building according to a code, any code in the world, and then you tested for the earthquake level, which is not the design one, but it's a much higher. In a nutshell, is a 2,500 return period earthquake. So the 2% in 50 years of that map of Kazakhstan that I was showing, whereby think about the southern west part, southern east part for you, southern east part is actually the region with big troubles. Peak ground acceleration of this test was 0.6 almost, 0.58. So we are in a very high seismic region. Let's see what happened. So we are testing
5, 4,
we are
3,
testing
2,
this building on the 3D shaking table. So the earthquake is actually a very strong earthquake from Christchurch with a high vertical acceleration coming from L'Aquila earthquake, 2009. So really a monster earthquake. And facades made of glass are detailed in a specific way. facades made of precast concrete heavy are detailed in a slightly different than usual way, and so forth. We have concrete timber, clay bricks. You're going to see also the interior parts. Going faster. These are the interior masonry bricks, and you would expect them to be completely destroyed. They're not, because after the shaking, during the construction, we provide some different detailing, some micro detailing, and so after the shaking, which is meant to collapse the building, these are basically unscathed. There's nothing going on. So faster, and I'm finishing. How much does it cost? You would be thinking too much. Let's try. I would like to explain to you what progress in this precast concrete technology means. So if you're thinking about the older phones and then the mobile phones, the older mobile, the mobile, the movable, not mobile, movable, and then the smartphones, and we're thinking about the cost, we could appreciate that the cost is much lower now. If you think about computers, that's even obvious, more obvious. A big computer, the desktop, the first 1980s, and then later on, the cost is lower. And the performances of the telephone, the phone up there, going to the right-hand side, and the computer, obviously the performance went to the sky, but the cost went lower. So what about concrete technology? Let me be more specific. Precast concrete technology. If we are using the pre-capacity design, pre-70 building, they were killing people. If we are using the plastic ingeminative approach, they are not killing people anymore. These buildings, they are protecting life, but they're not protecting themselves. If we are now moving to lower damage technology made of precast concrete, we are able to protect the business, protect the investment, protect the life commodity, protect the continuity, give resilience to our cities. So how much does it cost? Let me just say in a nice way, no, nothing more. So it will cost less, I can tell you, because we did many. But it would be important just to send the message that it does not cost anymore. Double negative, it does not cost anymore. So basically, you should be able to use a much higher performance type of building with equal cost. In English, we say that is a no-brainer choice. It's a choice that does not require a lot of thinking. I like to thank hundreds, to be honest, thousands of people who have been helping through these developments through the years. We're talking about 25 years in any continents, a huge network. Specifically, we pushed very hard, starting from San Diego back into Italy, and then we pushed very hard in New Zealand. And through the earthquakes, we got also a lot of teams coming from different countries to come and help us, and that has been extremely highly appreciated. After the earthquake in Canterbury, the reconstruction went through low damage technology of any sort, base isolation, the seepage devices of any material, as well as rocking system, again, in any material.
So I'm actually recording the registration,
So
but let me see what happened.
Tell you, I thank you
Maybe
very
it's
much,
better to do
Kia
in a
ora.
different
Thank you
way.
for your attention, and grazie per l'attenzione. The registration is continuing. I will be there live with you in few seconds. So have a very good one in your endeavors, and I'll talk to you soon in a few minutes. See you very soon.
Hello, everyone. I don't know if you can hear me.
Yes, we can.
So thanks for everyone for the patience in listening.
Большое спасибо за внимание, с которым вы слушали презентацию.
I would have been delighted to be there and speaking directly with you.
Я бы с огромным удовольствием хотел бы лично здесь присутствовать и делиться своим опытом и энергией со сцены.
I hope the message was clear. There's a lot of information in that presentation. Thank you very much for the translator.
Я надеюсь, что вы смогли составить себе структурированную картину, поскольку понимаю, что презентация была максимально информативной и наполненной очень теоретическими выкладками. Надеюсь, что вам понравилось. Большое спасибо за перевод.
I will be very happy to answer to any questions.
Если у вас есть какие-либо вопросы, я буду рад на них ответить.
One message I would like to pass on is that you have all the capability in the precast concrete industry in Kazakhstan and in Central Asia to do what we have already done in the other parts of the world.
Хотел бы отдельно отметить важный момент. Вся ваша индустрия сборного железобетона в Казахстане, в частности в Центральной Азии в целом, обладает всеми необходимыми ресурсами и возможностями для реального и практического воплощения тех новейших технологий, о которых я рассказывал.
So we all, and specifically ICCX, will give you a challenge, one challenge, which is we give you 3 years to prepare and develop, and we are going to work together, one of these buildings, a low damage precast concrete buildings. 3 years, no more.
Я лично и организаторы выставки, конференции ICCX бросаем вам вызов. Мы даем вам ровно 3 года, ни днем больше, ни днем меньше, чтобы за эти 3 года вы реализовали конструкцию по принципу проектирования сейсмостойких зданий с низким объемом, с низким уровнем повреждений.
But please ask questions or clarification. I would be very happy to have a bit of interaction.
Если у вас есть какие-то вопросы, я с удовольствием готов их обсудить.
Thank you for the first one.
Я
Спасибо
хотел
за
бы
первого
задать
смелого
вопрос
человека.
про объемно-блочное домостроение и вот влияние на сейсмику и как это влияет.
I would like to ask about the block, also volume frame block structures. How do they behave from the seismic point of view?
If I can ask back, do you mean the beam and columns, the frame?
Вы имеете в виду объемно-блочное?
Блоки вот полностью как коробка. Вот,
Like precast, like you have a module, fully precast module.
Okay, I understand.
And
So
you just
no,
put,
stay there.
like
Stay
typical
there.
construction in the Soviet time, you know.
Okay, yeah. So if you think about the 3D block, I understand what you mean. The prefabricated construction, yes, they are not bad. Honestly, they are not bad.
Честно говоря, они не так плохи с точки зрения сейсмостойкости.
They are not what the community today wants. The community today wants open space, so a larger span.
Дело в том, что блочное домостроение, в частности, в целом блочной конструкции, не соответствует современным тенденциям и требованиям архитекторов, поскольку с архитектурной точки зрения люди хотят открытое пространство. То есть сейчас пространство организовывается с минимальным количеством перегородок и ограничений. Поэтому они, возможно, и неплохо работают, но именно проектирование, архитектурное проектирование идет в другую сторону, получается.
So what we have been trying to do is to have 10 meters by 10 meters at least of length between structural elements. So you can have much more freedom to enlarge your rooms, your living rooms and everything else.
То есть так называемая свободная планировка, и наш минимальный стандарт — это свободное пространство 10 на 10 метров, чтобы можно было по своему усмотрению координировать, проектировать, планировать пространство, помещения, разделять их.
But it's a very good question, and I give you an example that what we have tried to do is to have a much longer block modulus, much longer, which is not fully prefabricated, but each element can become a two-story, two-base type of construction system. So starting from a much longer, a larger modulus, you can still recreate full prefabrication.
Несмотря, спасибо за вопрос, хороший вопрос. Можно посмотреть в ту сторону, что если мы будем использовать блоки большего размера, удлиненные, которые нам позволят реализовать концепцию свободного пространства, это, как я уже упомянула, это не будут полностью сборные железобетонные блоки, но в целом, если мы используем блоки большего размера, вполне себе двухэтажное здание можно строить подобным образом, таким образом воссоздавая блочное строительство.
Any other question or curiosity?
Еще какие-либо вопросы?
Здравствуйте. Большое спасибо за информацию. Ваша технология, я немножко опоздал. Ваша технология, каркасно-монолитное строение можно использовать, да? Каркасно-монолитные.
Can we use as frame in situ construction? Your technology can be used, or he was a little bit late for the presentation. Thank you for the very informative presentation. And the question is if your technology is suitable for frame in situ combined construction.
Very good question. The
Отличный
answer is
вопрос.
yes.
Ответ да.
Prefabrication has many advantages. So my preference would be to go for prefabrication. But we had design buildings, I did in New Zealand, where, for example, columns could be cast in situ, whereby walls can be cast in situ. So you can still produce a cast in situ or cast in situ partly and precast partly version with the post-tensioning, and they still can do the rocking system.
Да, ответ да. Несмотря на то, что, конечно, я предпочитаю сборное железобетонное строительство в силу его определенных преимуществ, но, в частности, в Новой Зеландии у нас был опыт проектирования комбинированных зданий, конструкций, в которых сочетаются монолитные каркасы или, например, монолитные колонны, монолитные стены. За счет использования нашей технологии с канатами постнатяжения мы даже при таком гибридном строительстве имеем возможность добиться упомянутого эффекта раскачивания.
It's interesting because I can follow, thank you to the translator, I can follow some keywords even during the translation.
Да, я даже во время перевода, я знаю несколько русских слов и могу следить даже за переводом. Maybe you can reply in Russian.
No, I cannot. But I could use Google to translate quickly.
That's exactly what I'm doing.
Very well, really. That's fantastic.
Спасибо.
Not really. Thank you very much.
Спасибо. Ну, приезжайте в Казахстан, мы вас
Come to
ждем.
Kazakhstan.
I would love to. I tell you, yesterday I was in northern part of Italy, in Trento, to explain the same type of technology in different materials. We can do in concrete, in precast concrete, in timber, in steel. The important part is that what we are speaking here about concrete and precast concrete. It's fundamental to really start doing in construction the new way. What I'm showing to you is not anymore the future, is the recent past and present. So again, the challenge is move ahead. You're already able to do it, and the progress, if you're embracing it, will allow you to do much better things. And I know that you can do it because I saw what type of construction system you're already able to do.
Я бы с удовольствием, с огромным удовольствием приехала в Казахстан. Я думаю, я воспользуюсь этой возможностью. Вчера я выступал в северной части Италии, в Тренто, с докладом, посвященным этой же технологии, но в приложении к различным материалам, поскольку мы ее можем воплощать не только в бетоне и железобетоне, а также в древесине, в металле и, возможно, в других материалах. И то, о чем я рассказывал, это не будущее, это уже наше настоящее, которое мы можем реализовывать вот прямо здесь и сейчас. И я с уверенностью утверждаю, что у вас есть для этого все возможности, все ресурсы, поскольку я видел, какие системы, технологические системы вы используете. То есть ваша техоснастка, технологическая оснастка полностью позволяет вам воспроизвести указанную технологию. Thank you for your answer.
Еще один вопрос. Спасибо доктору Стефану. Здесь тоже участники с Кыргызстана. Я хочу задать вопрос. Вот этот предохранитель, который можно заменить, у вас металлический, а можно сделать его, как в автомобиле, масляные амортизаторы, чтобы не менять, постоянно работал?
The question, can you hear me?
Amortizator, I got it.
Like in the car, oil filled, like concerning your metal fuses that you mentioned, the question is, can you make it like those oil filled in the car, so that you do not have to replace the fuse, just...
Yes, absolutely yes. So in fact,
we do call the plug and play, when we're explaining to non-technical people, we call them shock absorber, like in a car. We really say they are like shock absorber in the car. Now, this type of, you see behind me, if you see, hold on a second, I try. Hold on a second, there you are. Okay, there you are, here, and you see just that's a plug and play in a real building, one of my buildings in New Zealand. So you can have that type of device for literally tens of earthquakes, so maybe you don't need to replace. But we can use viscous damper, which are very similar oil-based or other type of liquid-based, but they are typical of earthquake engineering. So you can use anything. They become more expensive, while these plug and play cost 15 euros, 15 euros.
Дело в том, что как раз то, что я называю предохранителем, я использую в презентации на широкую публику. Конечно, по своей сути это демпфер, это амортизаторы, которые действуют ровно так же, как в автомобиле. В целом, да, можно использовать не совсем масло, а просто высоковязкую жидкость. Это ведет к удорожанию таких амортизаторов. Возможно, вам не придется их менять, но вот как я показывал за своей спиной, вот там с нашей проекции получается слева в углу сверху, это как раз один из примеров такого предохранителя, такого амортизатора, работающего по принципу подключи, работай, установи и работай. Наши металлические амортизаторы, предохранители стоят дешево, это 15 euros. It was 15 euros or dollars?
Yes, 15.
Euros or dollars?
Euros, dollars, same thing.
Окей, да, евро, доллар, в принципе.
Say US dollar. Just one important comment, and please repeat it if you can, that I really appreciated also the last question, but everyone. The last question was very good because the target, our target, is to make earthquake engineering simple. So you don't have to think that these are strange technology. These are normal precast concrete technology that you can do precast concrete normally, and we are just modifying with a post-tensioning strength, a steel post-tensioning strength, horizontally or vertically, and external rebar, two things, post-tensioning and external rebars. You're doing precast concrete in your same way, and we are just with these two concepts, we are improving significantly the safety and the resilience. But it's absolutely traditional way with some extra things.
Очень интересный вопрос, большое спасибо. Хотелось бы подчеркнуть то, что предлагаемая технология не означает чего-то революционно нового, потому что наша задача сделать сборное железобетонное строительство и производство максимально простым для людей, максимально простым и понятным в реализации. Это совершенно конвенциональное, стандартное сборное железобетонное производство и строительство, которое дополнено двумя важными элементами, которые обеспечивают сейсмостойкость и безопасность в сейсмоопасных зонах. Это в первую очередь постнатяжение, использование арматурных канатов постнатяжения вертикальной или горизонтальной проекции, и это стержневая арматура, которая как раз в сочетании с постнатяжением дает нам нужный эффект и безопасность. Подчеркну еще раз, что это стандартная процедура, всем знакомая, с небольшими модификациями.
Здравствуйте.
Thank you very much for your answer.
Мы производим трехслойные железобетонные панели. Я бы хотела спросить, есть у вас в практике или какие соединения, узлы вы можете нам предложить?
Простите, трехслойные вы сказали?
Трехслойные, железобетонные, с утеплителем.
We are producing 3 layers, also sandwich panels with insulation. And I would like to ask what kind of connections you can offer, what kind of systems, components, joints you can offer in this regard.
Thank you, Spasibo. I don't know if it's right. Thank you for your question. Yes, even in the sandwich panel, we developed a large sandwich panel that can be used as walls. as a structural walls. And again, if you're using post-tensioning, either inside the panel, the sandwich, or outside, you can have exactly the same type of behavior. So your sandwich panel can be developed in a similar way. The whole point is not to make things monolithic, because you're attracting troubles, you're attracting stiffness and strength, while it's allowing them to move, but controlling the movement by using cables and reinforcing dissipators.
В приложении к трехслойным изоляционным панелям, термоизоляционным панелям применяется такая же технология. Мы можем выпускать их большего размера, использовать как структурные, конструктивные стены в здании, располагая либо внутри них, либо снаружи канаты постнатяжения, которые дают нам как раз эту необходимую свободу движения, поскольку самая наша главная задача – это отойти от монолитного строительства, которое дает нам жесткость и целостность, монолитность конструкции. Нам требуется определенный люфт, определенное движение, которое мы получаем как раз за счет использования технологии постнатяжения. И контролируем как раз это раскачивание за счет канатов постнатяжения. В принципе, это возможно использовать трехслойные стены абсолютно так же, как конструктивные стеновые панели.
Something that comes to my mind, I think a previous person was saying, you should come to Kazakhstan, and I said I would love to, and I'm sorry that I couldn't. So I don't make promises because we risk not to maintain it, but I make a wish. I wish I would be able, within 3 years, to come there, because you have 3 years of time to try to develop one building in such a way, and if we try to do it together, I will have the good excuse to come to Kazakhstan. How's that?
Возвращаясь к предыдущему вопросу и приглашению приехать в Казахстан, еще раз подчеркиваю, что я с огромным удовольствием это сделала, извиняюсь за то, что не смог присутствовать сегодня. Давайте заключим сделку. Вы помните, я дал вам 3 года на реализацию моей концепции рассмотренной технологии, и я не обещаю, поскольку в наше время сложно обещать, я рискую не сдержать это обещание, но я выскажу пожелание. Я от всей души постараюсь и хочу приехать в Казахстан в течение этих 3 лет. Это для меня будет как раз ваш вызов, будет для меня стимулом вместе с вами добиться поставленной цели.
Buonasera, Stefano. Holger here. Actually, I cut it short. So on behalf of the organizers, I'm inviting you to come next year on stage alive. So you can continue these discussions with the people here. And I think looking at the interest, this will certainly be the best solution. So take my invitation already now, December 3-4 next year, you will be here. We are expecting you live on stage.
Thank you very much to everyone, for you, for the organization of ICCX, Olger and team, for the translator. She has been extremely patient. And thanks to all of you for listening. Hopefully we will see you soon. Do some reading if you can, and then when I will come there will be easier way to go deeper into the details.
От имени организаторов волевым усилием я вынужден нашу дискуссию прекратить из-за соображений графика и наших планов, но мы приглашаем Стефана в следующий раз выступить на конференции в следующем году здесь. Очень надеемся, что вы сможете присутствовать и приехать. И, разумеется, благодарю вам за эту презентацию. И видя, какой интерес она вызвала среди аудитории, среди публики, скорее всего, в живом общении дискуссия будет еще более интересной, более информативной и наполненной. Ответная речь Стефана была о благодарности организаторам, благодарности зрителям, вам, слушателям, за ваше внимание, благодарности переводчику за терпение и большое спасибо всем.
Извините, можно еще один вопрос?
Okay, one more, the last question.
Там вы показывали, что разработали пособие по дизайну сейсмостойких зданий.
You showed the manual, the design handbook, the complete design process of the 5-story building, as far as I remember.
Их как-нибудь можно получить у вас на платной или
Is there any way
бесплатной
to
основе?
get for free or for a fee this manual, this handbook, for this design
Yes,
handbook?
so that design handbook was prepared with the New Zealand Society for Concrete, and it's on sale from the Concrete Society. What I can do, maybe, we can think about it and organize it with ICCX. Maybe we can organize, let's say, a Russian version, English language version, but I need time. So if there is enough interest, we could consider to make that becoming a project, and by next year, maybe we can have a version that you people can use.
Этот кодекс, ну, точнее, этот проектировочный конструкторский справочник был разработан в сотрудничестве с Новозеландской ассоциацией бетона. Он на английском языке, он находится в свободной продаже. Есть такая идея, если это будет интересно и востребовано, подготовить русскую версию этого справочника, чтобы все желающие могли с ней ознакомиться. На это, конечно, потребуется время, но можно это организовать в рамках совместного проекта и к следующему году презентовать русскоязычную версию, например. Но в целом справочник можно приобрести на английском языке.
Спасибо. Тут еще коллеги попросили спросить еще один вопрос. В еврокодах заложены ваши разработки?
Are Eurocodes accounted for in your technology? Yes?
Yes, the other way around. The FIB Model Code 2020 is pushing very much for sustainability and for repairability. If you translate that, then I will say the next slide.
Не еврокода заложено, а немножко наоборот. То есть бюллетень ФИБ, Международная федерация бетона 2020 года, очень сильно продвигает тему экологичности.
So the design handbook is at this stage based on the New Zealand code, but it can be used in any Eurocode, Italian code. I know that in Kazakhstan you're following the Eurocode, so it is fully compatible as a technology, and you can absolutely design it using a Eurocode compatible philosophy.
Он базируется на новозеландском кодексе, который очень строгий в силу актуальности этой темы, поэтому он абсолютно совместим с любыми СНИПами, кодексами Европы, еврокодексами, итальянскими нормативными документами. Поэтому если вы опираетесь на еврокодексы, то вы, безусловно, можете использовать эту технологию, она полностью совместима.
We need to finish, so I leave it with a clarification because it's an important question. All the buildings that I showed you, some of the buildings that I showed you, were from New Zealand, Italy, US. I showed you from South America. So each of those countries were able to use the technology compatible with their own codes. I'm sure that you can do the same.
Перед тем, как попрощаться, хотела бы акцентировать внимание на следующем. Все эти здания, которые я вам сегодня продемонстрировал, были возведены в Новой Зеландии, в Италии, в Южной Америке, в США. И они все соответствуют требованиям местной нормативной документации, местных кодексов. Поэтому я уверен, что в вашем случае не должно возникнуть абсолютно никаких проблем.
Спасибо от всех слушателей. Еще раз спасибо большое.
Thank you very much.
Спасибо and arrivederci.
Arrivederci. Ну, наверное, чтобы я не скакала лишний раз, от своего имени, от имени организаторов поблагодарю вас. Огромное вам